Or goers, welcome back. Okay, so today we're going to talk about Claisen and Dieckmann condensation reactions. So this should be a pretty short video, but first I just want to talk about one last aldol example that we have over here. All right, so clearly it's an aldol because we have two ketones and we have an aqueous base like sodium hydroxide, so we're going to know that this is under thermodynamic control. So we're expecting an alpha-beta unsaturated carbonyl. So we have two alpha positions. We have alpha 1 and alpha 2. So if I did the numbering scheme from alpha 1, it'd be 1, 2, 3, 4, 5, 6. So clearly the enolate is going to be formed at alpha position 1, not alpha position 2, because if alpha position 2 formed the enolate, we'd have a 4-membered ring, not the 6-membered ring. All right? So we can rationalize that our enolate is going to be over here, and then that enolate is going to attack in here, form that hydroxyl group, and then we're going to do a subsequent dehydration. So let's just draw two cyclohexanes together, fuse together. Okay, so if I were to continue my numbering scheme throughout, so this is 1, 2, 3, 4, 5, 6. This would be 3, 4, 5, 6. And 1 would be over here, and this would be 2, and that would be 1. All right? So the new bond is between 1 and 6. So the alcohol would be over here. We had a ketone at position number 2. All right? And now this is why I wanted to talk about this one. We have a choice about where we can dehydrate that alcohol and put the alkene. So we have, let's just do, I'll do maybe highlighting colors. We have the choice of doing it in yellow over there. We have the choice in doing it red over here. And we have the choice in doing it orange over here. So any of those options could work. So we think about alkene stability. So most of you probably would have thought to do the tetrasubstituted or the orange one because that is the most stable alkene. However, we always want to dehydrate to where that alkene is in conjugation with the carbonyl, because in this situation, I'll write it out in words, conjugation outweighs alkene stability. Conjugation outweighs alkene stability. Okay, so it doesn't matter how substituted that alkene is. Sure, it probably does matter a little bit in the sense of like a mono-substituted versus a tetra-substituted. But in this case, we only have tetra or tri-substituted, and then the tri-substituted one is in conjugation, so that's even more stable than just a plain tetra one that isn't in conjugation. So always pick the one that's in conjugation with the carbonyl. And that pretty much sums up all of the aldols. All right, so let's move on to Claisen considerations and Dieckmann considerations. So in these types of reactions, it's the same thing that we've seen with aldol and the intermolecular version of aldol, except now we're just going to do it with esters. So what are the requirements? Well, the first requirement is that we need to have at least 2 alpha protons. That's always a thing, and that will make sense in the mechanism when we do that in a second. The base that is used matches the alkyl portion of the ester. So sometimes we see like NaOMe, so NaOMe. Well, the OMe section matches the alkyl portion of the ester, so there would be a methyl group attached there. If I saw NaOET, that means there would be an ethyl group attached there. All right, so those bases just match the alkyl portion of the ester. The reaction occurs in 2 distinct steps. So we saw with the aldol reaction under thermodynamic conditions, like above over here, we saw that it was, just one set of reagents, so sodium hydroxide and water. Here we're going to see it's two distinct steps, and that will also make sense in the mechanism. So the product of step 1 is going to be an enolate anion. That's the end product. And the product of step 2 is going to be the neutral beta keto ester, and that's the result of a protonation step. And we'll see that again when we do an example of the mechanism. Also, step 4, enhanced acidity of alpha protons following condensation. So let's rationalize why the alpha protons would be more acidic in a Claisen condensation. So it's the same rationale with the aldol reaction, but let's just say I had, this condensation, all right? So then the protons here, so let's just say this was my starting material, this ester. All right, so these protons are, these protons over here are acidic because they are located in close proximity to an electron withdrawing group, which is the carbonyl, or more specifically the ester. Now when we add, during a Claisen condensation, another ester, we have induction for both of those electronegative groups. So now the acidity of this hydrogen is even more so than it was before. So we can do some extra steps with our end products of Claisen condensations, and we can add alkyl groups by enolate alkylation, and then we can even do ester hydrolysis to form the carboxylic acid and subsequent decarboxylation. So I think step 4 is very important. If you guys are going over synthesis, I would definitely know the steps of doing enolate alkylation followed by ester hydrolysis and followed by subsequent decarboxylation. It is a very common series of reactions in a row. We'll see it in this example at the very end, this example over here. We'll see that, and definitely useful in synthesis. So let's just jump into a couple examples. So over here, let me zoom in. So this is a not uncrossed and undirected Claisen condensation. So we're going to form the enolate at this position, and it's going to attack into a molecule of itself. So I always like to arrange my enolates like this. So we have a ethyl group down here, and it's going to add into another equivalent. So let me just draw, the mechanism for the first one. Okay, so I'll draw the mechanistic areas in red. So the enolate's going to attack into here and push those electrons up. So the product of this step is going to be okay? And then the next set of mechanistic arrows are going to be the lone pair electrons on the oxygen, alkoxide anion, that kick off the ethoxide, and that is possible. We don't have to make it a better leaving group because we are under basic conditions. So then we form this product. And don't forget it's racemic at that position. But so we would think that at this position, so we did have the removal of OET minus, we would think that we are done with this product, but that is not the end product of step 1. What happens is that since we just kicked off that ethoxide group, that ethoxide can hang out in solution and still deprotonate any leftover alpha protons. That's why 2 alpha protons are required in Claisen condensations, because this happens in the mechanism. So really, the product of step 1, in terms of your mechanism, would be an enolate. So that is the product of step 1. Product. So in a mechanism, that is the most commonly missed step for getting to do this extra deprotonation step. So sure, we formed the same product here and here, but there is ethoxide that is kicked off in the mechanism, and that is going to form an enolate after step 1. That's why there's an extra step 2 now, which is hydronium. So now hydronium in solution can just be taken up by that, enolate that was just formed, and now we form back that fully protonated beta keto ester. So that's what I meant by neutral beta keto ester. It doesn't have a charge on it. And now we're chiral. All right, so that is the end product of that reaction. And don't forget, we would have a racemic mixture. Okay, so that is the mechanism for this. I would definitely know that last step. That's a key common mistake for most people. All right, so let's just do the next one. So let me make some more room. All right, so we are now over here. Okay, so let's look at this one. I'm sorry that they're so cluttered together. So let's first look at the alpha positions of both and see which one is going to form my enolate and which one isn't. So over here, that's my alpha position. Let's call it alpha 1. Over here, I have another one that's alpha 2. So alpha 1, do I have any hydrogens or any alpha protons? No, I do not. So this is not going to be the enolate. When I look at this ester, do I have any alpha protons? Oh, no, I don't either. So therefore, no reaction is going to happen. Right? So remember, you need 2 alpha protons to be able to do this condensation reaction, and there are not 2 protons available to do so. All right, so no reaction. That was easy. So now let's take a look at a Dieckmann. So this is a ring closing reaction. So let's both look at our alpha positions again with respect to the ester. So alpha 1, alpha 2. Alpha 1 has no alpha protons, so that will not be my enolate, but alpha 2 has 2 alpha protons, so it will be my enolate. So if I were to just draw in my carbon count, it'd be 1, 2, 3, 4, 5, 6. So we're going to have another cyclohexane fused with a benzene ring. So I always draw that structure first. So it's going to be my benzene and then my cyclohexane. Let me just keep my numbering scheme here. 1, 2, 3, 4, 5, 6. So at carbon number 1, we have just that ester still. Okay, and then at carbon 2, there's nothing, carbon 3, nothing, carbon 4, nothing, carbon 5, we have 2 methyl substituents, and at carbon 6, we have that carbonyl, and this is the tert butoxide that gets kicked out, so minus TBUO, that gets kicked out as the leaving group. All right, and that is our molecule, but do not forget that we are chiral at that position, so we would expect both wedge and dash orientations coming off of that ester. All right, and that's that. All right, so let's move on to these examples. So here's another example of a Dieckmann. So here, let's look at this alpha, alpha 1. Here, let's look at this one, alpha 2. So they both have 2 alpha protons available. So that means that we can form the enolate at both positions, and we can have 2 different products based on this attack. So this is an undirected aldol reaction. So let me just show you. I can do attack from this enolate into that carbonyl. Likewise, I can also do attack from this enolate attacking into that carbonyl. Both of those will form 2 distinct products. So let's just do that over here. So I'll just do the red product in red. So let me just erase all of this. So here we have these sets of enolates over here. So the carbon count would be 1, 2, 3, 4, 5, and 6. So I would have a 5 carbon ring, 1, 2, 3, 4, 5, and then I have that 6 carbon ring that's attached to it. Okay, and if I keep my numbering scheme consistent, 2, 3, 4, 5, so 1 would be here, okay, and we're going to attack into carbon number 6. So off position 1, we have our ester. Oops. So it would be at 2, at 4, we didn't touch that center, so we can keep the stereochemistry there. At position number 6 is where we generated the loss of methoxy, so the methoxy anion, so that got kicked off, and this is our molecule, but do not forget that it is racemic. So that is the result of this enolate adding into here. So I will just make sure that that is the red product. All right, so now let me do the blue product. Okay, so if I generated the enolate here, that's 1, 2, 3, 4, 5, 6. So I would have a, oops, room over here. I would have a 5 carbon ring again with that 6 carbon ring. And let me make sure my numbering is consistent. So it's 1, 2, 3, 4, 5, 6. So off position 1, you have that ester. At position 2, you keep the stereochemistry of that ethyl group. Nothing on 3, nothing on 4, nothing on 5. And number 6, you're going to retain that carbonyl again with the loss of methoxy. And don't forget that you are racemic at that position. So you can see that we have 2 very distinct products. So whenever you have 2 enolate anions, you do have to take into account the 2 different sets of undirected attack. All right? So I hope that makes sense. Take a second and make sure you do the mechanism. I think that would help. All right. So let's just do this last step right here. So we have this series of things, and I think this is very useful in terms of synthesis because you can do these separate reactions at like 3, 4, and 5. These are steps that you can do after the formation of the Claisen condensation for the beta-keto ester, and we'll just jump right in. So the first thing is we are going to generate the enolate. So we have OME, oops, I did that backwards. We have MEO, and we form the enolate there, and we're reacting with formaldehyde. So the product of step 1 is complete deprotonation of that enolate, and then we are going to attack into this carbonyl, so we are going to form this product. Okay, and this is going to be, okay, so we formed this product, all right? So then step 2 is going to be adding in some sort of base. Okay, so we have sodium methoxide again, so that's going to form another enolate at that alpha position because remember we enhance the acidity of those protons there by adding in a hydroxyl group. And then we're going to do nucleophilic attack with this alkyl halide to extend the carbon chain. So I can just rationalize it adding another methyl group over there. So that's the product of step 3 right here that I'm drawing right now. Okay, and then the product of step 4 is going to be ester hydrolysis. So that's going to be turning this molecule into a carboxylic acid, at least the ester. So I can just rationalize that this is going to happen. Okay, and I corrected this on the worksheet, and I didn't get to do it here before I made this PDF. But step 5 should have been PCC. And then step 6 should have been heat. I kind of forgot to put that PCC in there. So this product of PCC would form that primary alcohol would turn into a aldehyde. Okay, and then the last step is just that decarboxylation step that we see over here. And I'm just going to make some more room because I ran out of space. And that last step is a decarboxylation step that splices out this carboxylic acid, so now we have this product. All right, and that is our final product, okay? So you can see we can take the beta-keto ester that we formed from a Claisen condensation and do a whole bunch of manipulations with that end product, such as alkylation at the alpha position, followed by ester hydrolysis to form a carboxylic acid, followed by decarboxylation. So that's a very common thing that you could see in synthesis. And that's it for Claisen and Dieckmann.